one thing that we understood is without disturbing the system, we can't do any measurement. So depending on that minimum disturbance that we can do during measurement, whether it is negligible or not, we define whether it is big or small, whether classical mechanics is applicable or not. Okay, that is the absolute definition of big and small size of the object. And again, that also taught us one more thing, that measurement outcome is ultimate. We can't say anything before that one. Even our superposition state also taught the same thing. Measurement outcome is ultimate thing. We need to design the theory so that again it gives some what you call idea about measurement outcome and probability of measurement of outcome. Before getting into mathematical derivation of uncertainty, uncertainty principle is mathematically derived actually. You know about standard deviation? Standard deviation. So standard deviation on x we are going to write. Again, I am going to do this one. Okay, in the first chapter, average x square minus average x the whole square, like that. Okay, we call it a standard deviation in case of continuous variable. Okay, so that standard deviation is called as uncertainty also. The same thing. Okay, sometimes I use uncertainty to quote uncertain things. Okay, sometimes I am going to use uncertainty value. Okay, I better to say like that. Okay, uncertainty value. So before, again, we can mathematically derive this one, sigma x into sigma px. Okay, that is greater or equal to h bar by 2, where h bar is the reduced applying constant, h by 2 phi. Okay, I hope you know that one. H bar is equal to h by 2 phi. Okay, we can mathematically derive this one. Right now, we shall try to understand uncertainty principle in some other means. Okay, because that will help us to understand that linear combination state also, superposition state also. Uncertainty is because of superposition state also actually. We will get to know that one, isn't it? There also there kind of uncertain things were there in case of double slit experiment. We don't know through which slit it is going to pass through, isn't it? That's also uncertain thing. So similarly, we'll try to grab some logical idea regarding uncertainty. Is that okay? So then we will go to mathematics. Okay. So we call this one as Heisenberg. Now we call that one as Heisenberg gamma ray microscope also. Look at here, there is one optics formula. Again, that optics formula depends on diffraction condition only. Okay, that optics formula that depends on diffraction condition only. So look at here, we have small, so two small objects which are separated by a distance d. Okay, let me take this d, and you have an objective of your microscope here. Okay, you have objective of your microscope like this. So then what you do here is, you are going to draw it like this. You are going to draw some angle theta here. Okay, the minimum separation that can be well resolved, that's nearly equal to lambda by sin theta. Lambda is the radiation that you use. So radiation should fall on that one, that it should go to the objective of the microscope. This is objective lens of the microscope. Okay, this is the half of the angle subtended by that objective with the objects. Is that okay? So this minimum what you call separation that can be well resolved, the minimum distance between any two object, small object, that can be well resolved. So that is nearly equal to lambda by sin theta. From optics, this is also diffraction idea. I hope you know this one. Okay, this is also diffraction idea. So I think there should be 1.22 something will be there. I am not taking this one because I need only orders here. Okay, I don't need any exact equation. Am I right here? So 1.22 lambda something would come, but whatever, it doesn't matter for me. Yes.
So I mean, this equation can be derived
from optics, a diffraction condition actually.
Diffraction condition.
Yeah, you just check that out in optics. Okay, I am going to use this one. Okay, so that's why I have drawn that one from optics. Okay, from optics. Now I'll come to Heisenberg gamma ray microscope. Look at it here. This is a thought experiment. Okay. Now in this thought experiment, we are going to take gamma ray because look at here. If lambda is small, we can have very good resolution, isn't it? So that's why gamma ray frequency is very high. Lambda is too small, so that we go for gamma ray while finding any very small so distance and all. So again we are doing so we will try to measure the position of the electron here. Okay, I have electron here. I have electron here which is moving along x-axis. Okay, let me define axis here. Let me define axis here. I cap, j cap here. Okay, let me define axis here. Electron is moving like this. So now what I do is I just exactly above this one I have objective of the microscope. Okay, I have objective of the microscope. So this angle is theta again. This angle is theta again. Is that okay? So now what I do is, again, when you are observing electron, this is the objective lens. Again, electron was moving along x direction. Let me take it like this. Okay, px of E. Electron was moving in x direction. So before measurement, then you shine light, not light, gamma ray actually. Okay.
Before measurement?
Yes. Tell me before.
Before measurement.
No. I mean, to measure only you should shine light, isn't it?
Yes.
Then you switch on your gamma radiation here, so that gamma photons will fall on it. Gamma photons are sent in this direction only, along x-axis only. Is that okay? So now what will happen is, this gamma photon, it will hit the electron. So again it will go in various directions, but it is received by the this objective lens with this region. Am I right? Whatever the gamma photon, so which are scattered in this range of directions. Okay, so that will be received by your objective of the microscope. Is that okay? So this is the basic idea. Okay. Now electron was moving along x-axis. Okay. No y component of momentum of electron. Electron was moving along x-axis. Is that okay? Now I'm trying to find its position. Again, x position only. If you are observing from here, means where it is along x-axis. That's what you are trying to find. Okay. This is x-axis. This is x-axis. Now look at here. What would happen here is, once again, so now according to optics I am going to write like this. Look at here, you can measure its position, but with some uncertainty, isn't it? You can't go below this one, isn't it? So there is some uncertainty, isn't it? Now let me take, so momentum of gamma ray, let me write it as h by lambda. Is that okay? I'll write magnitudes of the, what you call, momentum of the gamma ray, that's h by lambda, where lambda is the wavelength. Is that okay? Now look at here. So again you are using gamma ray to find the position of the electron here along x-axis, where it is. Okay. So now look at here. While finding that one, you have some uncertainty that is decided by optics. That depends on incident wavelength and all. Is that okay? That uncertainty in the measurement of x component of position, uncertainty means error. So again within that limit, again, so you can have position anywhere within this limit. That's what I am saying. You can't have accurate x position because of the limit by optics. Is that okay? So that's nearly equal to lambda by sine theta. Is that okay?
Yes.
That is nearly equal to lambda by sine theta. So now next one is, yeah, again you can find position of the electron with this uncertainty. Can I say like this? With this error, because this is limited by optics. Incident wavelength, objective, theta, how big objective lens is, depends on theta also. You may find it is somewhere here, but it has some uncertainty. Okay. So it has some uncertainty, plus or minus something. We write like this, 2 centimeter plus or minus 0.1 centimeter, isn't it? We are going to write like this in case of scales and all. So like that, very similar to that one. That is decided by optics actually. Now next part is uncertainty in the momentum. Look at here. Now after scattering, photons are moved in a different direction. Okay, let me write p gamma here. P gamma. They are moved in a very different direction. Okay. Again various direction with angular part is 2 theta actually. So what will happen is, now I am going to find, look at here, if a photon which is moved in this direction, okay, if a photon which is moved in this direction, just take that idea. So then, so I'll write it as P gamma vector. What is its x component of the this one? Suppose if this is theta, quickly, that is mod P gamma sin theta. This mod P gamma will not change. Okay. If a photon which is moved into this corner of the objective, then its x component of what you call its momentum is P gamma sin theta. Okay. So similarly, if a photon which is moving like this, again you have photons which are which can choose any of these directions. Okay. So now if a photon which is moving in this particular direction, so if this is theta, so then again this will be P gamma mod P gamma sin theta, but negative, because it has negative component of what you call
Why
momentum.
take mod of this company?
No, this is P gamma vector. This is P gamma vector component.
Okay.
So again, if photon moves in this direction, it has no x component. It has 0 x component. If photons moves vertically upward, it has 0 x component. If photons moves like this, it has some x component. Okay. Actually, next experiment is the best way to deal with this one, but this is historical one, isn't it? Heisenberg gamma ray microscope. Now look at here. You are measuring photon, so there is uncertainty in the x component of momentum of photon. Can I say like this? If all photons reach the same point, you can say it has no uncertainty in the x component. But some photon reached here, some photon reached here, maximum number of photons reached here. So photons reached here have got px 0, px gamma 0. Photon reached here, px gamma mod p gamma sin theta. Photon reached here, they have p x gamma, x component of, I'm just observing x component of its momentum, not y component. Is that okay? So that's equal to mod p gamma sin theta with maybe negative sign, is that it? Photons received here have got range of x component of momentum. Can I say like this? Is that convinced? Speak out, anyone on Google Meet.
Yes, sir.
Yeah.
Sir,
Yes.
sir, these all are the scattered photons.
Yeah, scattered photon. These all are scattered photon. Is that okay? Now look at here. So that's why whatever I am writing, uncertainty in the x component of momentum, in the x component of momentum of measured photons. That means there may be some photon which are scattered in other direction that is not measured by the microscope. Okay. So that is, look at here, that is nearly equal to, I'll write it as delta px only, that is nearly equal to, I'm going to write mod py sin theta. Let me explain this one, okay, because this all gives some mathematical idea later, it may be helpful. Okay. Now look at here, more number of photons reach here, less number of photons reach here actually.
Yes.
It's a kind of diffraction pattern again if you take. Now again, if you draw what you call, so probability distribution, okay, so probability of getting so py, sorry, px, I'm not talking about y component, px versus px, okay. So you will have again you will have this one minus mod py sin theta plus mod py sin theta, but this probability distribution will not be uniform. Okay, it will be, I think, maybe like this, because you may receive less here, more here. Is that okay? Or maybe equally probable. You can take like that again, because I don't have any rules here to say. But since it will form a kind of diffraction pattern, that's why I have drawn that one. Okay. It's a kind of diffraction pattern of this object. That's why I have drawn that, so that kind of curve here. Okay. So that means more probable here, less probable here. That's why what I do is, I'm not writing uncertainty as a full length. Now look at here. If suppose photons were scattered with equal probability, photons were scattered with equal probability, then that probability distribution you can write it as a constant. Am I right? Equal probability.
Yes.
if suppose photons are scattered with equal probability of x component of momentum, I could have written like that, then full length itself is uncertainty in that case. But it is not happening like that. It will happen like this actually. Again, so that's why what I do is I'll take half of the length as uncertainty, approximation only again. I'm writing nearly equal to. Is that okay?
Yes.
Now look at here. Electron was earlier moving only along x-axis. Now because of scattering of photon, okay, its x component again earlier before photon hitting the electron, it has well-defined x component of momentum. Because it was moving along x-axis, we can take that situation. Am I right? You can have stream of electron which is moving along x-axis with a well-defined what you call kinetic energy, isn't it? You can have that one. Earlier, electron was moving along x-axis with a well-defined what you call momentum. After scattering of the photon, look at here, that's x component of momentum changes, isn't it? It will recoil. If photon moves like this, it may recoil like this, isn't it? If photon moves like this, it may recoil like this. So that combination of the motion, so it may move like this, like that. Okay, you can take some conservation of momentum like we did in case of Compton effect. Is that okay? So that's why what happens is there exists uncertainty in the x component of electron. Because we are applying uncertainty to electron, isn't it? Totally we need to, at the end we need to connect it to uncertainty of what you call electron only. So that's why. So because of this scattering of the photon in a different direction, so because of recoil, electron also will possess some uncertainty in its x component of what you call momentum. And that uncertainty is same as this uncertainty. Because that uncertainty occurred because of this scattered photon only, isn't it? Are you getting my point?
No, sorry, repeat again.
This uncertainty in electron x component of momentum, it happened because of scattering of photon,
Yes.
isn't it? So that
Collision.
after collision, just as in case of Compton effect. Is that okay? So that's why uncertainty there exists again after collision by the photon, there exists uncertainty in its x component of momentum that happened because of collision, because of recoil. Okay, that uncertainty is same as this uncertainty. This is equal to uncertainty in the x component of momentum of electron. Yeah, definitely. It's because of momentum conservation only. This uncertainty is equal to that uncertainty. It's because of momentum conservation. Because so it also had well-defined x component of momentum earlier. It also had well-defined x component of momentum. Now x component of momentum is what you call have got some range for this photon. So similarly, so because of momentum conservation, I think you can work it out. If you see closely, you can work it out. Suppose take one photon which moved here. What is the change in x component of momentum? Suppose one photon moved here. What is the change in x component of momentum of electron? By finding this one, I think you can prove this one. But I am taking this one as a statement right now. Okay, not much important for me. Okay, that is equal to, this uncertainty is equal to uncertainty in the x component of uncertainty in x component of momentum of electron. Is that okay? When these two are equal, so what was this uncertainty? This uncertainty was uncertainty in the position of electron. Okay. Now look at it. I got uncertainty in the momentum of electron, x component of momentum of electron. Now I can write delta px here. Now again, now it is not for photon. Okay. I found it by calculating it for photon, but that is equal to for electron. So that's why this is nearly equal to, so py, mod py, what you write, h by lambda, h by lambda sin theta. And I found both of this quantity for electron only, but I found this quantity from photon idea. Indirectly. I found this one indirectly. I found this one directly by optics formula. And when you multiply them, delta x, delta px of the order of h bar. So if you write inequality here, suppose you write inequality here, uncertainty in the measurement of what you call position, that is decided by optics, again that is greater than this one always. It will never be less than that one, okay? It will be always greater than this one. Then if you multiply, you will get inequality there. Suppose if you need inequality, you can write greater here.
Okay.
Uncertainty will be more than that.
More than that means.
Worst case.
More than that means comparing to.
So more than D minimum. More than D minimum. Uncertainty may be more than D minimum.
Okay.
Like that. If you put inequality, there comes inequality. That's it. Okay. But anyway, we are thinking about order, not H bar. H here. Okay. I've taken H here. Even if you take this one as twice, because you had a range of value, right, from negative to positive. Even if you take twice, you may get one more factor 2. That also follows uncertainty principle. You don't have to worry. Okay. You can take twice also. Suppose if you are worried about that one. Now, if you try to decrease one, other will increase. Is it okay? If you try to decrease one, other will increase, so that product will be nearly equal to Planck constant. Okay, so we say there exists uncertainty between position and momentum. Okay, we have better experiment, okay, than this one, because we find this one quite indirectly. Okay, yeah, I think using momentum conservation, you can show this equality. Okay, try that one if possible. Now what I do here is, I'll go to, yes.
So this is kind of an observational error, right? I mean, if we try to observe something, then we only get this error.
Yeah. Now yeah, exactly. It feels like in this experiment, you could have done some better apparatus, isn't it?
Yes.
But it's not like that. Okay. One thing is, this is what you call derived equation. This is derived equation. I think that will be convinced in the next one.
Okay.
So this you will get your answer in the next one. Okay. You may say that we can do some better apparatus, again very good resolution, so that again if you want to do good resolution, look at here, what you have to do, you should make aperture very big. Am I right? Usually, if aperture theta very big like that, I think, isn't it? So if you make aperture very big, photon will have more what you call range of photon, whatever received, it has more x component of what you call.
Yes, I mean, whatever we do, we have to eject a photon or scatter a photon like
If
that.
you-
This
if
scatter
you-
photon, there will be uncertainty.
Again, so to make what you call more better what you call, if you want to decrease delta x, that's equal to what was that, lambda by sine theta. So theta is between 90 degree. Okay, you don't have to worry, within 90 degree. Okay, so now what you do, you try to increase this theta, that means this angle, by making aperture big and big. Then what will happen? So delta px, that will become high and high,
Yes.
isn't it? So what is this one?
H by lambda.
H by lambda. Suppose h and lambdas are constant here, sine theta, isn't it? You don't have, if you try to measure one thing with more accuracy, other will be affected, so that product is constant. Is that clear?
Yes, sir.
Oh, you again, yes,
We can't measure the position and momentum simultaneously.
simultaneously.
Momentum letters, and we can define whether it was the.
Yeah, again, if you are worried about only one, if you do the measurement, you will find some position. You will find some position. If you do the momentum measurement, you will find some momentum. Okay, I'll tell you in the next experiment. That's the best way. So it looks like you can do a better apparatus, so that both of things can be measured accurately.
So
It will not
in
happen.
that apparatus,
Huh.
when we observe that one, we will see only position. If I want to see position, then I can say position of momentum.
Momentum you can judge from this range of photons and all, isn't it?
But since we have sin theta.
No, again, momentum, it has a well-defined momentum before collision, am I right? It had a well-defined momentum. So what I am saying is, if you try to measure position more accurately, momentum will be more and more uncertain. That I can definitely say. Here I can't make the arrangement to make momentum uncertainty small.
No, actually my point is that delta x means lambda by sin theta, and delta px also means sin theta by lambda. We have two same equation factor.
No, suppose if theta increases, if this decreases, that increases. That's what I am saying. Now, in this arrangement, you don't have what you call arrangement for measuring momentum more accurately. It's a measurement of position actually. Position of, no, you don't have any arrangement here. Again, you can make a aperture very big so that you can measure this one more accurately. But you have to compensate other one. Here, this arrangement is not for measurement of momentum. Are you getting my point? But you can find momentum uncertainty. How much uncertain momentum is if you try to measure position more and more accurately.
So if I measure momentum, I mean alternative.
Again, but somehow then you have to pay the price here. If you try to measure that one accurately, you have to pay the price here. That I'll show in the next experiment. Yeah. No, uncertainty is decided by nature. It's not a measurement problem actually. That I'll convince in the next experiment.
Yes.
It is decided by nature, natural phenomena. You can't prepare a state at all. I'll get into state. Here I can't talk about state of the particle, okay? Because those states ideas are important. Look at here. In this one, this double slit, this uncertainty, I'll try to convince most parts so that later only thing that is left out is mathematics.
Okay.
That's how we do. Yeah, that's why uncertainty is it's a inbuilt natural phenomenon. Okay, it's not because of our measuring apparatus. I'll improve and I'll make it uncertainty field. That will not work because that is derived mathematically. Okay, we shall see that one later. Now, single slit diffraction. So we have studied that again. We say electron have got wave nature and all, isn't it? So that's why so diffraction pattern should happen, isn't it? If you have a single slit, okay. Now what I do here is I'm going to have two arrangement. One is so quite big slit width, quite big slit width, okay. In other arrangement, I'm going to have slit width very small, and I'm going to take this one as y-axis. This one as x-axis, I cap, j cap. Okay, this is y-axis. Vertically upward is y-axis. Horizontal is x-axis. Okay, let me take like this. Now let me shoot electron. Okay. So now electrons are shooted so that it is equally probable anywhere here. Okay, it is equally probable anywhere here. Is that okay? Electron is equally probable anywhere here. That's why I'll write this one as delta y. Now, when you shoot the electron very randomly, you don't know where it is along y-axis. You don't know where it is electron along y-axis. You have some uncertainty. Okay? When it passes through slit, electrons are prepared with uncertain y position. Can I say like this? Because electron can be anywhere here. Just like in case of double slit experiment, it has again it can be either psi 1 or psi 2, isn't it? Like that, it has a range of y position. It can be any. It can have any y position. Can I say like this? Between these two. Suppose if you take this one as 0, y. So suppose if this is y-axis, if this is 0, this will be delta y. Okay. Are you getting my point? Electrons are prepared with a state which has y uncertainty. You can't say electron is moving only in this y position. You can't say electron is there in this y position. Okay, you have some y uncertainty when slit width is big. Now in
How can you prepare a state then?
no, state means once it passed through, that is the state that is prepared. That's what I'm saying. Once electron faces the slit, it's a state that is prepared. Isn't it? Once electron faces double slit, if you are not observing, state is prepared, psi 1 plus psi 2. Superposition state is prepared, and you will observe the consequence, isn't it? Is that okay? Yeah. Now look at here. So because of this one, you get like this. You don't get much diffraction, but little deviation, am I right? Little deviation, almost like this. Is that okay? Almost like this. Maybe secondary, first maxima, secondary minima may exist, but you can't find that one in this situation. It's very big. And observe here, so once you prepare electrons with what you call more uncertain y component of position, okay, more uncertain y position, okay, look at here. So almost all electrons moved along x-axis, am I right? This is x-axis, isn't it? So this electron might have moved with some angle to this one. These electrons, this might have moved with some angle, but its y component of momentum is almost 0. Am I right? So this again, electron which moves horizontal, it has 0 y component of momentum. Okay. So this has py 0. This electron. Okay. This electron may have some py, but small, isn't it? So this electron may have minus py, but small, isn't it? Little bit deviation, I haven't shown properly, okay? So that's why range of py, uncertainty in py, so that is small.
Okay.
Is that okay? So delta py, that is small. I hope you know about vector. Look at here, if suppose if you have vector A here, okay? Vector here, x-axis, y-axis. Okay, so now it has some component here. Okay,
Yes.
it has some suppose this vector is along this direction. Suppose if vector is vertically upward, it has no horizontal component. If suppose that vector is horizontal, then there is no vertical component. I hope you are getting this idea. Components of the vector, I am talking about component of the vector.
Yes.
Okay, it has only px component, x component, it has no y component, but this has slight y component. Are you getting my point? If you just resolve this vector, okay, it has slight y component. If you just resolve this vector, okay, it has slight y component. Are you getting my point?
Yes.
Electron in this beam and this beam, this has slight y component, very small. You can see this one, am I right? Suppose if you resolve, I hope you know about vector, resolution, component and all. Now, so this will happen. If this is high, okay, if this is high, look at this is quite high in this case, am I right? Delta y, this is high actually. So simultaneously, look at here what happened. This is small. Here there is no what you call. Look at here. How I know that this is small, delta py is small? Because I know that this is not spread throughout the screen. This spread only very narrow region. I am not doing any measurement here. I am not observing here. I am not switching on any light here. By seeing the electron on the screen, I will get to know that yeah, this is small. That's why it's not deviated. Are you getting my point? Since delta py is small, that's why electrons are not deviated. It is received somewhere here,
Yes.
isn't it? So I mean, or I can say it has almost well-defined x component of momentum. Where again, so almost all electrons are moving along x-axis. I can say like that by seeing the screen, isn't it? Is that okay?
And whatever we pass through the slit, all those.
Almost all, they have very less y component of momentum range. That's why that I can say after seeing the electrons at screen, isn't it? I don't have to measure anywhere here. I don't have to disturb the system. Now look at here. We are preparing a states, okay, in which if it has well-defined y component of momentum, almost well-defined y component of momentum, zero value is also well-defined. Almost 0, am I right? Y component of momentum is almost 0, isn't it? For all of these electrons. That's also well-defined value, isn't it? If you prepare a state with if you want to prepare a state with well-defined y component of momentum, its y component of position will be ill-defined. Ill-defined. Are you getting it? Ill-defined, not well-defined. Okay. Now look at here. Come to this one. Now again you shoot the electron with equal probability here. Now what you did is you made delta y very small. Delta y very small. So then what will happen? What will happen? Okay. Some electrons moves here in this direction, some electron moves like this. You will have a diffraction pattern, okay, whose probability distribution is like this, isn't it? You will have a diffraction pattern. Now observe carefully. Electrons moved in this direction. This has py0, because that is moving along x-axis. Electron, again, suppose let me take this angle theta. Okay, electron moving in this direction. Very less number of electrons reached here. Okay, but electron moved in this direction. Look at here. If you measure, make it as theta, so this has some py. Am I right? This has considerable amount of py. Electrons which are moving in this direction, this has negative py. Theta. Am I right? Suppose if you take electron have got some momentum, let me say that is Pe. Okay, P is the momentum of electron. This will be Pe sin theta minus Pe sin theta. So this will be plus Pe sin theta. Suppose this is Pe. This vector is Pe vector. You can write Pe sin theta here. You can write minus Pe sin theta here if this is Pe vector. So this is again y component. Okay. So Py is equal to this one. Py is equal to this one minus Pe sin theta. So can you write these things, or later try it yourself? Okay. Now look at here. This range become more. Am I right? Than here. You can see now electrons are moving in a again different range of momentum actually. Is that okay? You can now look at here. Since each of our measurement is disturbing the system, once electron reached here, suppose electron is reached here, it has some y component of momentum. Okay. Once you find that electron reached here, after finding electron here, you can't say that it has uncertainty. How do you got it as uncertainty? When you shoot a freshly prepared electron, so some electron come here, some electron come here, some electron come here. That means they are prepared with indeterminate momentum states. Are you getting my point? Now look at here. So let me take you to earlier idea. Earlier idea is if you do the measurement, the system is disturbed. Am I right? Similarly, if you find the electron somewhere here, it is collapsed, that it has taken one of the momentum value, isn't it? If you detect electron here, after detection, yeah, you know that from here it came from this direction. It has this what you call component of momentum, isn't it? So that's why look at here. Since our observation always makes it to collapse to one of the state. Okay. So what we have to do is we should take freshly prepared system. We should take freshly prepared system. Wait a second. We should again look at here. With one electron, you can't talk about uncertainty. If you have if you talk about one electron here, okay, that electron have got very small y, and it will reach somewhere, and you can say, yeah, it has well defined y component, isn't it? After you found that electron there, isn't it?
We have to compare.
With one measurement, you can't talk about uncertainty. You have to do repeated measurement. Once you find electron here, on that electron you don't have any way to measure again, isn't it? That's why in any measurement, not only here, in quantum mechanical measurement, okay, to talk about uncertainty, probability, whatever, since each of our measurement will lead to collapsing kind of thing, will each of our measurement disturbing the system, okay, just like I talked about electron earlier, am I right? Electron falling under gravity. Since each of our measurement is disturbing our system, you should take identically prepared system. Okay, measurement on the system is disturbing the system. If you do the next measurement on the same system, you are doing that one on the disturbed system. Are you getting my point?
Sir, repeat again.
If you do the measurement, you are doing the disturbance. Without disturbance, you can't do the once. Okay. I have one system. You do the measurement. First measurement.
Okay.
This system is disturbed. If you want to do second measurement on the same, you are doing on the disturbed system.
Yes.
Its state is not as earlier. Are you getting my point?
It will change.
First measurement itself, what you call disturbed system. If you do the second measurement on the same thing, you are doing on the disturbed system, not freshly prepared system, not earlier state.
Not freshly prepared state.
Huh. So that's why we will try to have freshly prepared state, identical states, identically prepared system, we say like that. Now, so all of the electron which you send here, which passes through this one, you send one by one. Okay, you send electron one by one here. Okay, each of those electron, I call that one as identically prepared system. Okay, so some electron reaches here, some electron reaches here, some electron reaches here. That says that again you are doing the measurement on identically prepared system. What you call, you are seeing on the screen means you are doing the momentum measurement actually. Is that okay? You are trying to find where the particle is located on the screen. That means you are doing the measurement of momentum here. Is that okay? So that means those freshly prepared system have got some uncertainty. You can't say where next electron is going to be reached. Are you getting my point? That is the uncertainty. You can say the next electron y position is somewhere here, isn't it? Very small. You are trying to make that y position very small, very certain, isn't it? You are trying to make certainty here, isn't it? But this will be uncertain. You don't know where it's going to reach here.
But sir, for a particular electron, we can find its momentum.
Yeah, for one electron, it will reach here, and you can say it has this y component.
Define its momentum indirectly, you can say.
No, for a particular electron, yeah, you can find the momentum, no doubt.
We can't for the electron, we can't get its momentum directly.
But wait a second. For a particular electron, wait a second. For a particular electron, before it is reaching the screen, can you say that it is going to reach here?
No.
That is the uncertainty. Are you getting my point? That is the uncertainty. Electrons are prepared with a well-defined y position, but ill-defined y momentum. Because of that one, you have a lot of spread here, and you don't have any control over it. If you say I'll make y component also small, or y component uncertainty is also small, you don't have any control over it. It's very natural diffraction phenomena. Is that okay? Now look at here. I'll talk about states now. I told in case of double slit experiment, my state will be psi 1 plus psi 2. Am I right? This also kind of uncertain. We don't know through which slit it is passing through. Now here also you are preparing a state. Okay, you are preparing a state which has well-defined y position. Again, now that is the translation state. Okay, here I am talking about either position state or momentum state. Okay, can you grab those words? Position state and momentum state, energy state, spin state. Are you getting my point? In quantum mechanics, we are going to define different state. Look at here. That wave function represents the state actually. This probability amplitude, whatever we say, that will represent the state. So actually, what I said is, so P is equal to mod psi square. Am I right? I said psi is the probability amplitude. I said earlier, a state itself is wave function. Am I right? State itself is wave function. I have written like that. Am I right in the earlier class? So again, the better word is wave function, or this probability amplitude represents the state. State, because state is the most general word. Ground state, first exerted state. Wave function represents that state actually. It's a more better word. Are you getting my point? So we say these are psi 1, psi 2 are translational state, isn't it? Translational states are represented by probability amplitude or wave function. We say like that. Are you getting my word? Translation state, whatever I called this one wave function itself as translation state, isn't it? I call like that. More better word is translation states, or states are represented by probability amplitude or wave function. That's the more better word. So similarly, I have a state here. Okay. Now I am not talking about translational or something. Okay. I'll talk about position state and momentum state. How my prepared state of the electron have got well-defined position, well-defined momentum. Okay. Now this state have got well-defined So position actually. Is that okay? Again, the same state have got ill-defined y component of momentum. Is that okay? I better to write like the same state have got it has got many states of it has a linear combination of many states actually of y component of momentum. Just like here it was linear combination of two translation state. Am I right? So here, again this uncertainty is hold again we are going to hide that one in case of state here. Psi state. If you write psi state here, okay. So that state contain, look at here, psi of px1 plus psi of px2 plus and so on. Sorry, y component. Am I right? We are talking about y component. Are you getting my point? This state, whatever you prepared, that has well-defined y component of what you call. So this state you can write it as. So that's a state of some y value, almost accurate y value.
Yes.
Or that range is very small. I'll say range is very small. You can't have very accurate one. You should have some opening, isn't it? Electron should pass through. So that's why it has very accurate what you call value. Let me write only y1 plus psi of y2 plus and so on. Okay, plus only very small range of y value. Let me say like this. It will not be plus. Okay, it will be integration. You will see later, because these are continuous variable, not discrete variable. Okay. It will be integration, but for a comfort I am writing summation. It's not summation, okay, it's an integration actually, because you have continuous range of y component of momentum. Or suppose I can write like this, summation over psi of py sum dpy. It has some range of the state, it has some range of what you call y component of momentum. Or it is a superposition of different y component of momentum states. So can I say like this? It's a superposition of different y component of momentum state. That's why if you do measurement, you get py1 once, py2 once, py3 once. Just like if you do the measurement, you will get either this translation state or this translation state. Are you grabbing my idea? But it is not a summation. Actually, it will be integration. You will find it later. But again, this integral here, it contains very small range. This integral contains very large range, because this is very small here. Py range is also very large here. Speak out.
So, sir, in case you want to define the momentum state, there will be defined momentum along x direction plus uncertainty in y direction, like the integration.
No, uncertainty in x direction also exists, but I am not concentrating on x direction momentum, x direction position at all. Uncertainty exists because again you have range of direction, okay, but I am not concentrating on that one. Here I am concentrating on y component of position, y component of momentum. Uncertainty exists between those coordinates, okay, px and x, py and y, okay. Here I am not thinking about y component of momentum or y component, sorry, here I am not thinking about x component of momentum and x component of position at all, okay. But I am preparing a state which has got very small range of what you call y component of position. If you do the measurement, the range of y that you may get, that is very small. Either this one or this one or this one or this one, very small range, okay. But if you do the momentum measurement on this state, okay, using freshly prepared system, you got range of y component of component value. State is same, but the state have got quite well defined y component of position, ill defined y component of momentum. That is uncertainty. You can't prepare a state with well defined y component of position as well as y component of momentum. Both cannot be, again, you can't prepare a state at all. Look at here, you don't have any control here. Do you have any control here? I hope you got some idea about states here, okay. No, how do you do that one? I mean, once you measure here, that will be disturbed actually.
Sir, where do we know?
Once you measure, again you are disturbing. It is not freshly prepared at all. But look at here. Look at the state here. Don't go for, you don't go for measurement. Again, you are doing measurement. What is, you are doing momentum measurement here.
Yes.
But you have control over this one also. In the earlier experiment, you don't have control over momentum part, isn't it? Momentum or position part. But here you have control. If you, yeah.
Sir, when hits the screen, we are observing the momentum or position?
Momentum. Again, because once it is hitting the screen, I know that it came from this direction. Am I right? It has this direction of momentum, isn't it?
But when it hits the speed of is zero, right?
After hitting, it will be rest. It is collapsed. I mean, it is disturbed. Again, on that one, you can't do any interpretation. Once it reaches the screen, its part is over. On that one, you can't do any interpretation. Are you getting my point? Its job is over. You have to take other freshly prepared system. Is that okay? I better to share old batch video again, because there you may get much more idea. Okay, so I think I did explain little more there.
Because
I don't.
when hit the screen, I can know the position.
No. Again,
But we are saying the momentum.
yeah, because you know that this direction. Am I right? That direction decides the y component of momentum. If you want to measure y component of position, you should measure here, isn't it? It is the state is prepared here, isn't it? So because of this uncertainty, y uncertainty, again here it got spread actually. Are you saying that here you have very large y range?
Yes.
No, it is spread because of this one, remember, but not here, isn't it? So soon after here, look at here, it is taking different direction. Suppose if you are not measuring, think like that. Soon after it is well prepared y, it got different y component, isn't it?
Yes.
If you try to prepare a state with well defined y component of position, its y component of momentum will be ill defined. Because of that uncertainty, you got a range here. Are you getting my point? It's not like that here you have wide range, here you have small range. You just think over just after the slit, isn't it? That's a very good question. Yeah, you read out some YouTube comment. Now look at here. So if you try to make delta y small, delta py will be big. If you try to make delta y, again, if you try to make delta py small, if you want to make delta py small, you have to make this one big. You don't have any control over it, isn't it? In this case, delta py is small, isn't it? In this case, delta py is high, isn't it? Wait a second, I'll quickly work out the mathematics, then you express this one. Because the exactly similar mathematics can be worked out here, okay? As that we did in case of earlier. Wait, 1 second. I'll just quickly work out, because this is as simple as that of that Heisenberg microscope, okay? So you have, this is straight line. So you have first minima here, okay? Your diffraction minima is here, okay? This is angle theta. This is angle theta. If electron is moving, look at here. Here we don't have any photon as that of Heisenberg microscope. We have only electron, isn't it? So this will have so this will be also theta. So this will be, how do I write? Mod, if I take this is PE vector, I can take it as mod PE sin theta. Am I right? So yeah, like that. So if I take it here, this is also theta, so that this is PE vector. So this is minus mod PE sin theta. Is that okay? This apparatus is to prepare some states and to measure it. Isn't it? Are you getting my point? Now if you shoot along y direction, it will go like this. It will not pass through this one at all. That may have well defined momentum or position. We don't know. We are preparing this one to do some, what you call, to have some idea, isn't it? That's why I am shooting along x direction. Are you getting my point? Wait, let me work out mathematics, then wait a second. According to optics again, according to optics, this is a diffraction, am I right? the first minimum condition, you know that if this is slit width, if delta y is slit width, any idea? Sin theta, sine of this angle, sin theta nearly equal to, I think lambda by slit width actually, that is delta y.
I think he's getting in
Diffraction, first minimum condition.
Grating actually.
Not grating, single slit diffraction, first minimum condition. Some approximation will also be there. Optics, from optics, okay? So then delta y nearly equal to h by, not h, what is that? Lambda. Lambda by sin theta, okay? So now what is delta py? Again you approximate that one as mod pe sin theta, okay? What is this pe? H by lambda. Is that okay? So then, so delta py from this one, I actually, you could have taken 2 pe sin theta because it is varying from negative to positive, am I right? Whole range is so 2 pe sin theta. But probability is not same, okay? It has high probability here, low probability here. So that's why taking the full range is not a good idea. You will understand this one when we work out some distribution problem, okay? Distribution, uncertainty, so standard deviation problem later, okay? So again, if all of these electron have got equally probable here, then you could have written total range as your uncertainty, but they are not equally probable here. More probable here, less probable here, okay? So that's why you take half of that one approximately as uncertainty in py, that is nearly equal to 2 mod pe sin theta. So sorry, 1 mod p sin theta, okay? I am taking half of the range, so that is nothing but h by lambda sin theta. Exactly the same equations came, isn't it, as that of Heisenberg microscope.
So this from optics.
This is from optics. So this is by analyzing this one, isn't it? This is by analyzing this one. So now delta y, delta py is of the order of lambda got cancelled if you multiply h. Is that okay? Here in this one, since particle is moving along this one, I am not worried about its x position, okay? X position and x momentum, because uncertainty exists between this one, sigma x, sigma px, sigma y, sigma py. We are going to derive like this, like that. Is that okay? Yes, speak out now. Now wait a second, let me finish one point. Look at the state, okay? State that we prepared. We prepared the state. We prepare a state where, look at here, this state have got very well defined py, that is nearly equal to 0, isn't it? But this state, its y position is, so y1 plus psi y2 plus and so on. It's not a summation, it should be integration, because it is not discrete one, isn't it? It is continuous variable actually, or you can write as integration of psi y dy, and I need to manage what you call dimension also. Anyway, we shall take care later, okay? Similarly, so in this one, this state, this has quite very well defined y naught. Let me take this position as y naught, okay? Not much variation here, but this state have got very psi of, again here this may give the wave function, will give you the information about x component of position, what you call momentum also, remember, but we are not worried about that one, just see the only one dimension part, okay? Psi p y1 plus psi p y2 plus and so on, isn't it? That's what I have written earlier, isn't it? Let me try to write a note on this one, okay, if possible. Because you can't, look at here, uncertainty, that doesn't mean if you try to measure one thing more accurately, other thing will be ill defined like that. No, not like that. If you try to prepare a state with one quantity, with one quantity more accurate, other quantity will be less accurate. Or if you try to prepare a state with well-defined y component of position, okay, that state will have the same state. That state will have y component of momentum ill-defined. Are you getting my point? It is continuous only. This is only for comfort. This is only to say that it is linearly combined. It is similar to the superposition state. Okay, this plus symbol, whatever I have written, in mathematics it will not happen like that. In mathematics it will happen like this actually. You will get to know. We will work out pure mathematics. Okay, but I am trying to push state idea. So preparation of state, that idea into your mind. One more thing is uncertainty. Again, because we do lot of mistake in applying uncertainty. Even many books does that mistakes. Okay. Uncertainty means you can't prepare a state with well-defined both quantity. If you prepare a state with well-defined, y component of momentum, okay, here states of the electron have got well-defined y component of momentum, almost well-defined. Can I say like this? So in this state, so y component of positions are ill-defined. If you do the measurement, either you get the y1 or you get y2 or you get y3, any range here. Are you getting my point? If you try to prepare a state with well-defined y position, okay, with very small range, that state will have ill-defined y component of momentum. If you do observation, so it may have py1, it may have py2, range of y component of momentum. That means you can't prepare a state with well-defined momentum as well as position. So we may think that uncertainty is about only measurement, isn't it? It's not about that one.
Yes.
Quantum mechanical state itself, follow this one. Quantum mechanical state itself follow this one.
So classically we think in our mind that it will like
Measurement. Why can't we measure? Isn't it? Classically we think like that. Why can't we measure? No, it's not. We can't prepare a state with well-defined both quantity at all. We can't prepare a state. This experiment is the best one. Again, I'll share so previous video. You watch that one again, because there I might have given some other idea. So they try to club idea and grab this one, because then almost half of the job is done here of quantum mechanics. Okay. Later thing is working out pure mathematics. You will have no problem. I don't have to go to any interpretation later. Okay. Yes, quickly ask.
Ashish said that just take screen very close to the opening,
Then also look at here. This deviation happened here only. Okay.
after imaging,
Here only. This deviation happened here only. This deviation, it happens here only. Try to understand state here. Okay. Idea of state here. So that next only thing is mathematics. Again, you will not have any physical part of the term. Yeah, quickly. Next one.
So Akash asked, uncertainty is in nature or in
Natural one. It's a natural phenomenon. This is derived one. Okay. It's a natural phenomenon. So just all of you note down Arya's statement. The state itself carry the uncertainty with it. Upon observation, you verify uncertainty. That's it. You can only verify uncertainty. You can't control it. Are you getting a point? Uncertainty is a natural phenomenon. You can only verify it. You can't control it. That's the best idea, isn't it? Here you have to learn one thing. You should not apply this uncertainty whatever the way you can. We create lot of quotes, everything, isn't it? Or again, even in some books also they apply uncertainty in that way. You should understand that one. Okay.